All right, welcome folks. Welcome to Colloquium, and welcome to folks on YouTube on the webinar. So today it's my great pleasure to introduce Yaser Sheikh. Yaser is the founding director of Meta Reality Labs in Pittsburgh, where he's been working on a lot of the stuff he's going to share with us today. And before that, he was a professor at CMU in the Robotics Institute, and also appointed in mechanical engineering. So Yaser still hangs out there at the university a little bit, but mostly at Meta, full-time at Meta. And I'll keep this introduction short by saying that, and I saw Yaser give a version of this talk in 2019. He called it metric telepresence at the time. I was just like completely blown away on many dimensions of like how you'd formulate that problem and how you try to attack that problem. And so we scheduled Yaser to give a talk in 2019. There was a wildfire, so it didn't happen like at the last hour because there was no power on campus, and then there was a pandemic, as you all know. So like that leads us to today. Okay, so this is the updated version of the talk. So without further ado, Yaser Sheikh.
Thank you, Ren. Thank you all for coming. So the question I want to discuss today or explore is what is Codec Avatar? To start things off, it's maybe hopefully obvious to everyone that humans are social animals, right? So in other words, how we live, how we're productive in our work, how we're happy in our social lives, all depends on how well and how we interact with other people. This is a scene which is, of course, familiar to everyone. A group of friends interacting, playing some card games. And you can see as a scene, this is flooded with social signals. You can see how James on one side is looking at Dan, who reacts by looking down below. His wife is reacting, this hand over heart gesture responding to what he's doing. James's wife playfully stealing a card. All of these gestures, their subtlety, they mean things to us immediately. We can sense what they are, and it's incredible how much we take from these sorts of signals that we send one another. Of course, the biggest challenge all of us have experienced personally over the last couple of years is how much distance interferes with social connection and social interactions, right? And this is, of course, not a new problem. The reason why we formed villages, cities, why we clustered together in this way is because of the value and importance of social interactions, in person, face-to-face social interactions that we all have. To overcome distance, we invented the postal service, and then perhaps the first great breakthrough was the telegraph, which allowed information to be sent instantaneously over distances, but just information, just messages. Telegraph itself is, of course, even persisted as a means of communication today as messaging. Messaging is a direct kind of technological child of the telegraph. Maybe the big innovation past that was the telephone. Now, for the first time, people were able to actually hear what another person was saying in real time, not just the content of what they were saying, but also all of the nonverbal information, the cues in the way they spoke, how quickly they spoke, how concerned or how stressed they were on the tone of their voice, how happy they were. All of that was captured for the first time. And it's a good kind of a basis to study a little bit further. Imagine there are two people, or there's a person who would rather live in, say, a city like Paris, but wants to interact with colleagues in Pittsburgh, a purely hypothetical individual. And what we did was invented a sensor, a microphone, that could pick up the range of frequencies that people speak at, and a speaker with it, which was able to reproduce the sounds that were captured by that microphone. And these were co-designed. The microphone and the speaker were designed to be able to capture the spread of audio frequencies that we can hear, and largely the ones we can produce. And the idea was to just transmit them in an analog way over distances to the speaker, to the listener at the far side. The key point I want to make in the slide to pick up is that the sensor data matches the display data, that what the microphone picks is exactly what the speaker puts out. And this is kind of key to this being adopted, in my view, as a global means of communication. That data was treated like that, like information. It was preserved, it was not mucked around with. What a person said, the transmitter could be assured to a large extent that what the receiver hears is what they said. So this aspect of signal integrity, that whatever the sensor sensed, the display displayed, This was key to it being adopted. And as I'll say, with the telegraph, a similar sort of a case. So what happened when we moved to the digital domain? This is where codecs arose. So what we did was we had the audio signal from the microphone go into an encoder. And then the encoder produced a code that was compressed, and this allowed it to be sent over a distance to a decoder that would then decode it to produce, once again, the speaker. The reason why we chose to implement encoders and decoders in this way was to reduce latency, to make sure that the time interval between when someone said something and when somebody else heard something was as minimum as possible, because bandwidth was related to latency. And we could compute the latency by just simply summing up the encoding delay, the transmission delay, and then finally the decoding delay. So the key point here is that sensors, the decoders, the encoders, the displays were all designed to minimize distortion and latency. These were the two measures that we designed the system for, collectively. And so let's look at what one of these axes looks like. Distortion, I just express it in this way as the mean squared error or the sum squared error between what the sensor picks up and what the display finally produces after going through the encoder and the decoder. And then the latency, of course, is simply the sum of the encoding, transmission, and decoding delays. So what is one point here? So let's say, for instance, you take something which has low distortion but high latency. It would sound something like this.
We did get some potatoes last year.
Can you guys hear it?
First year trying it, it wasn't the best. But we also tried to grow carrots.
All right, so maybe I'll describe distortion through words, which is not ideal, but I'll try it. So obviously it's what you hear a pure signal sound like, what an audio signal should sound like. What high distortion sounds like is some garbling, some sort of white noise on the audio. That's what something which would have low latency and high noise sounds like. And what codecs are essentially a trade-off between these two spaces.
Last year. Our first year trying it wasn't the best. We also tried to grow carrots.
What codecs do is they trade off between these two. You can compress more to reduce the latency but increase the distortion. And the quality of an audio codec is determined by the extent that it minimizes distortion and latency. Right? That's how you measure it. The more you can sort of trade these off and break the trade-off between them, the better we consider a codec to be. And ultimately, that's the pressure that we try to push, with the hope that if we can reduce distortion to zero and latency to zero, it should be indistinguishable from a real interaction. And so the next sort of step in global communication was video conferencing. And once again, it follows a similar sort of a model. Now the sensor has not just a microphone, but a camera as well. And the display not just has a speaker, but has a monitor on there too, a visual display too. And once again, just like you had with audio, the video goes through an encoder to produce a video code, produces a decoder, and then that video is reproduced on the other side. Once again, just to note, the sensor data matches the display data. That's why codecs, video codecs, and audio codecs are considered largely to be compression. In fact, they are compression systems. And once again, just like we had with audio, there's an additional term, some weighting between the video loss and the audio loss, and you try to minimize distortion and latency. And the quality of a video codec here is determined once again by the extent that it minimizes distortion and latency. So does it mean that an in-person conversation is approximated or equivocated once you minimize distortion and latency to zero? And it turns out, like all of our experience over the past couple of years tells us that's not true, right? Anyone who thought that the experience of attending a meeting with Zoom was similar to what they experienced as an in-person interaction, I think very few would say that were the case. One sort of obvious one is lack of eye contact, right? Like this is what we experience when we're talking to someone, whereas what we really want is something like this. You want eye contact. That's sort of maybe the very basic element of a social interaction, is to feel that someone is looking at you and they're actually connecting with you as they look into your eye. So this sort of basic aspect of social interactions is missing, and we've all missed it while we've engaged in Zoom. Another sort of example becomes much more apparent is in a multi-person setting. So this is Jason trying to speak with 4 people, and it's unclear whether Michael over here is paying attention to what Jason is saying on a second screen, or if he's just looking outside of the window, or if Salim here is paying attention or playing Minecraft. It's impossible to tell, right? There's no way you can tell. Contrast the feeling of this, like if you were a person on a Zoom call seeing that versus what you remember in a scene like this one, right? Like where you are with friends, where you are in a group of people with them. What you sense and what you draw out from that. So the first challenge in trying to break the constraints of video conferencing is the display, right? Like how do we produce a display that allows you to share a space with another person or with other people, to feel like you're there and that interaction is indistinguishable from being there with other people. One solution, one sort of exciting project coming out of Google in the last couple of years has been Google Starline, in which they have a 3D display where you can sit and you can feel like there's a person over there in 3 dimensions. And I'll play like the result. You can see as he's looking at her, the different views produce a sense of 3D. And this really gives you a sense of like being present with another person and at least solves the problem of eye contact. But yet you are still behind the screen. You're still separated from that other person. There is still no way for you to share the space with this other person or with other people in the environment. You're still locked behind that screen. An alternative which has emerged in the last 5 years is 3D displays in the form of AR and VR, right? So in 2016, there were a bunch of headsets released, Oculus Rift, the Sony PSVR, Google Daydream, the HTC Vive. And since then, there have been kind of like a mess of headsets that have arrived, right? Culminating, of course, in the latest and greatest Quest Pro, which is available right now in stores. And then, of course, with AR, there were the Microsoft HoloLens, Magic Leap, and much less sort of like recognized as within the spectrum is spatial audio. So Apple released the EarPods, and this can give you a sense of three-dimensional audio space directionally, in 3DOF only so far. In other words, as you move your head, the sound source will move with you, as opposed to be embedded in the space. But this is just the start of a change in how we listen to things as much as how we see things as well. So the challenge that we have is to use displays like this one, AR and VR headsets, to enable authentic communication in these sorts of artificial realities. And this sentence actually is our goal, and it also sort of highlights the challenge that we have. Authenticity and artificiality are antonyms, they're opposites of one another. And that's our challenge. We have to fool the world's most sophisticated perceptual systems. Human beings looking at other human beings they know and fooling them into thinking that they are there with that person. So how they look, how they move, how they sound, that's the bar that we have to cross. This has history. So Henry Fuchs and others conceived of this. I mean, of course, there are others before them, Marvin Minsky and others. But Fuchs had this paper in 1993 where he conceived of a practical method of capturing what a person is doing and then having a doctor in a remote site maybe view the person remotely. So this was a concept that was proposed by Henry. Takeo Kanade and others in the 90s also realized a system like this at CMU. With the virtualizing studio. And actually in Berkeley, there was a system by Rizuna Abashi and her colleagues, the tele-immersion system, which used motion capture to allow some sort of remote interactions as well. But really, I think the big breakthrough came in 2016 with Shahram Azadi's group at then Microsoft. And they proposed this thing called holoportation, where for the first time with the HoloLens, in real time, you could interact with people. This system required the installation of 24 cameras in an environment, but it was the first time it was demonstrated this could be done with a lightweight headset in an environment in real time. So it was a real breakthrough. This is a recent result that we showed. What I'm about to show you is a 3D avatar of myself, rendered in real time, my full body, the background, and what you can't hear is the spatial audio as well. So I'll just play this for you to see.
Left, look right, look up, look down. It can express facial expressions and also subtle movements of the body, like hand movements, as well as challenging body poses, which involve self-contact that we do all the time when we're interacting with other people. Now,
so just to be clear, this wasn't sort of like a 3D point cloud. It wasn't a 2D rendering. This was actually a fully realized avatar. In other words, it was drivable and controllable, and it's fully rigged as well. And as you saw, rendered in real time. So that's kind of like the problem before us, right? So what we want to have, which is very different from the systems we've had before, are now the viewer, for the first time, influences what they see. With audio compression, with audio signaling, with video signaling before, no matter what you do, what it showed you was exactly what the sensor saw. Now this is different. Now what you see depends on what you do as well. And you're not restricted to just seeing one view of the person. It is up to you what you see of that person. You can walk around, you can see them from behind, you can see them from the front, you can get closer, you can get further away. And what you hear also depends on what you do. So this is one way in this problem becomes significantly different from that before it. And of course, the display has many challenges of its own, which I won't speak on, but field of view is one example of many, right? You want to be able to see a lot of the scene. And it's not clear why this is important for social interactions, but it actually is, as this example shows. The red square is 45 degrees, which is roughly what most AR systems are like right now. The green one is larger than most VR systems, but look at where in the field of view the two people are if you want to talk to them. If you have an AR system, one of them is certainly outside of the field of view. And even if you have 80 degrees, they're away. If you have 120 degrees, it starts to come in, but they're still fairly close to one another, which is not what it would tend to be like. And this is what you see in a real interaction. When I'm having a conversation with Ren, out of the corner of my eye, I am actually looking at what Bruno's doing. Is he paying attention to me? Is he not? That's an important signal to how engaged the audience is, or how engaged the group are in as well. So field of view, resolution, and frame rate, these are all aspects of the display that are important to get right. Now, the question is, if that's the display, right, a binaural display, what sort of sensor can match this display? In the way that we had a microphone for a speaker, in the way that we have a camera for a monitor, what is the sensor that can match this display? That's one of the key challenges in realizing this goal of social interactions at distance that are indistinguishable from real interactions. Of course, the most direct one is, since you're able to see the person from any direction, you'd have sensors in every possible location in the scene. You have something close by, behind the person, all around the person. You try to sense the person from everywhere. But is that even possible? Right? It's not. Because sometimes the hand might be in the place where you want it, or if you have many, many sensors, one might occlude another one. And of course, the other sort of like challenge over here, which I'll talk about, is we have to do the same sort of like, ask the same question about audio as well. Where can the microphones be placed to be able to produce the data that you could match the output? And the fact is that the sensor data can never match the display data in this case. It'll always be the case that you will have to hallucinate or imagine what the person is doing from a sparser set of data. So in this way, codecs in this sense, the encoder and decoder, or the algorithm that we'd use to infer what's happening, has to do more than simply compress and decompress. It has to understand the behavior in some way. It has to understand what the person is, how they're moving, and what they're doing. I didn't speak of illumination changes, because the person must, of course, be in another environment as well. So this is an example of the same person. We have a room with LEDs all around it, so they're being illuminated in all sorts of ways. And you can see in each time the person looks different. So what sort of sensor would be able to sense you and then place you in another environment? That is another sort of impossibility. In practice, what we have, for instance, in the Quest Pro, this is what the system sees of the person's face, right? So I'd ask, like, if I gave you this view of someone, can you tell what the person looks like or what facial expression they're making? It's quite challenging, right? Because this is kind of like an incomplete jigsaw puzzle. It's even worse with the body. So what you're seeing on the bottom three, so these images are all what the person's face shows, and then the top two are what the hands of the person or the upper body of the person is doing. And from that, we have to infer this, like what is the person's full body doing. So I'll play this for you. Just see how much of his body movement you can infer. So the question is, from these views, this input that we have, can you infer what the person is actually doing? And that's, of course, extremely difficult. So in this case, we have asymmetric communication. The sensor data does not match the display data. And this is fundamentally the challenge in accomplishing this goal. So how do we do this? How do we actually solve this presence function, where you're given the sensor data from the transmitter, some information of the environment, the display, the sensor data from the receiver, where they're looking at the person, and produce what the display should show. So this is something which we call the presence function, where it takes as input the receiver sensors, the transmitter sensors, and the environment state, and produces what the receiver's left and right eye should see, and what the receiver's left and right ear should hear. This function should be maybe somewhat familiar to the graphics folks. A version of this, maybe a similar version of this is a BRDF, right? Like a reduced version of this, which says, given the incident illumination, given properties of the object and the environment, it tells you what the outgoing light would look like. This is that, but for an entire person, and that for audio as well as video. So it's kind of like a generalized version of this. And really the core question is, how do we design sensors, encoders, decoders, displays to minimize distortion and latency? So that gets us to the question of this talk. What is a codec avatar? So let's open up the black box. So a codec avatar is also a pair of functions. Just like any other codec, it's an encoder and a decoder. It's a pair of functions that produces a code. That code goes into a decoder to produce the display. But it has a special sort of structure. One is that the decoder depends on what the receiver is doing. In other words, what you're doing when you listen or look at your transmitter changes what you see. And then the second is the environment you're in is something that changes based on what that's set as. So since you and I are going to be in different environments, therefore you can either be in my environment, or I can be in your environment, or we can both be in a third environment. That has to be set in. So it's a pair of functions that disentangle the transmitter, the receiver, and the environment signal. So it has this property that it disentangles between these three conditions. And the goal is to minimize distortion and latency for telepresence. The goal is to make the interaction indistinguishable from a real one. And we achieve that by minimizing distortion and latency. This is sufficient to make it indistinguishable. So once again, that's a note, right? If you reduce the distortion of the signal, you reduce latency, with the codec avatar, it should be indistinguishable from a real interaction. Of course, there are some physical limits. The speed of sound is one. The speed of, light is one, right? As you're communicating over the internet, how long it takes to get across the antipodes of the Earth is about 60 milliseconds. And so that's one sort of physical limitation. There are others, of course, as well. And the hope, of course, is that we have a target which is above the physical limits, but induces behaviorally equivalent in-person conversations. So one sort of stance which a lot of people take is, as long as the behavior is plausible, as long as what's rendered is plausible, that's good enough. But the statement I'm making over here is a bit different. It is important that we achieve a level of distortion and latency that makes it behaviorally equivalent, not perceptually indistinguishable. Meaning, if I perceive your behavior to be natural looking, that's not good enough. It has to be behavior rendered that doesn't change the nature of our conversations. And it's not clear whether that target is below or above the physical limit. And this is, in fact, a question of research that still has to be established. It's easy to define the latency. Once again, you can just sum up the encoding delay, the transmission delay, and the decoding delay. But a much tougher question to answer is, how do we measure distortion? And why is distortion even important? So this is an example. If I ask you if this is a real picture of Danny or a rendered one, you might say it seems plausible. But this is actually a rendering of her in a particular state that was actually erroneous. This is what she was really doing, right? And if I flip between these two, the difference is subtle. But I would contend that the message being sent by these two subtly different facial expressions is actually quite large. This is a somewhat flat affect. This one is a little bit more open, inviting, asking something. And my reaction to this might be a little different. But then her reaction to that might be a bit different. And the entire story of the conversation would be very different as a result. So subtle differences and distortion are important to minimize. This is another example. Subtle differences, but the meaning of the expression changes, and how you react would likely change to it too. So how do we measure distortion? The actual answer is we don't actually have a very good means to do this. This is a research space, and one of the challenges in this is to come up with proper definitions of what distortion is. The best I can say is we want to minimize the average reconstruction error across the entire set of signals of any behavior that the transmitter is doing, every environment that the transmitter can be in, and any observational state the receiver can be in. We want to average error across all of these in some way and still be able to minimize distortion. So in a sense, this is sort of like a framework in which I think about the genealogy of the work that we've done so far with Codec Avatars. The very first version was in 2007, and I'll show you what that looks like. This is the very first version. We've had some issues with video, so I'll play this. Hopefully it works. Here, Shui and Jason are having an exchange. What I'll point out is in the very beginning, Jason sort of smiles a bit, and that isn't quite captured, but I'll play this for you to see.
Okay, second question. So I was looking up iterative reweighted least squares, iteratively reweighted least squares, and so there's this W which you input in front of every single. Also in linear regression, you have y minus ax. You have to minimize that.
So you can see it sort of captures their likeness. You can see the dots on Jason's face to help with tracking. The affect is quite flat, right? Like there was none of that smile was captured, none of the expressions in either one. It was more or less mouth flapping, but at least it looked and generally moved the way you would expect. And how did we do that? So let's just look at the decoder to start with, which is what this primarily was. The decoder is something which we want to, as I'd mentioned, disentangle the expression, the view, and the environment. And we do that by training neural networks to do exactly that. We pioneered the use of, now we call them neural rendering methods, in 2018. And I'll show what this means, right? So what that means is we want to be able to programmatically change what the appearance of the output looks like separately for the expression. So here first I just simply change the expressions of the transmitter. So the person changes their expression only. Then we can jointly change the environment and the expression. And what happens over here, you can see it's being relit. High frequencies as well as low frequency and shading and shadows are preserved. And we can also change simultaneously all three of them. The view direction, the environment, and the input behavior as well. All three of them together. So this facility of disambiguating or disentangling the receiver, the transmitter, and the environment, that's one aspect of these decoders. This is in fact the defining aspect of these. And how did we do that? This is a device that we built in the lab. It's essentially a machine to do that. Produce the data to enable us to train decoders that can disambiguate, disentangle the observer, the receiver, the transmitter, and the environment. What you see over here is a room with around 170 high-resolution, high-frame rate cameras. And as I said, the intent of this is to disentangle the transmitter, the environment, and the receiver. And of course, there's been a history to these sorts of capture systems. I mentioned the one at CMU, but there have been many of these built over the years across the world. And most of these are actually still in active use. And just to give you a sense of the difference in terms of the size of capture, what you see on the horizontal axis here is the year they've been built, and on the vertical axis is the amount of data that they produce. And this is sort of like in 2016, we built our first system, Mugsy. As you can see, it was a big jump forward in the amount of data we were able to produce. The Shopticon, which I'll talk about, is for the full bodies. That was even a larger jump. Then we revised, so Google built one of these domes in 2020 with a large jump too. We built Mugsy's third version in 2020. And then finally we built the Shopticon, which is much larger, a couple of years back. Why is this important? So these systems allow us for the first time to sample not just a few expressions that the individual does. We actually sample an hour and a half of each individual. And we do this from every viewpoint. And then we also do this in every lighting condition to get environments as well. This is an example of the data captured. You can see every viewpoint. And in fact, you have enough resolution to see what he had for lunch too. Individual hairs we are able to actually disambiguate in this view. There's sufficient resolution for that. Okay. And that's in a sense what this does, right? We are trying to sample the space between the receiver, which means the views that the person does, and the transmitter in terms of the expressions or the different states the person can be in. And each of these, sort of like a row over here, is one view, and the person does the entire expressions, and we capture that person doing them. And another row here would be another view of those same expressions that the person does. A column over here would be every view of a particular expression that the person makes. And we capture about an hour of these from 170 views. So here's another case where minimizing distortion. When we train these neural networks, what we train them to do is actually minimize the error of every single pixel here. We try to, you see the rendered versus the real. I'm flipping between them, and you can see that this actually tries to reproduce pixel for pixel what the person did. So that was the receiver and the transmitter. We also want the environment. And why is the environment important? This is an example of myself in an environment which I obviously am not in, right? And you can tell I'm not in that environment because of the lighting, because I'm not lit in the proper way. And an occlusion is another important aspect to make sure you feel like you're there. So this, to account for the environment in Illumination, we built this a lighting system within there, which follows the work that Debovic did for many years on the light stage. So I'll play this. Once again, in addition to all of those cameras in the space, we also have individually controllable lights. And so now, not just, we don't just span view and expression, we also span lighting and expression. And in fact, we span all three of these together. We can change the expression, the lighting, and the view direction. And this is, in essence, a disambiguation of these three axes. The three things that we want our decoder to be able to disentangle. This is an example of the data set produced there. And here's the result. So what we have over here is inside VR, this is a capture within VR, where we move a light source inside the 3D space, and it relights the face of the person. All of this is happening through a network in real time. So I'll play this for you to see. I should stress that seeing this inside VR is very different from just sort of experiencing this in a 2D screen. But nonetheless, I hope it gives you a sense of what it feels like. And here's sort of a relighting to a completely new environment. And in terms of like evaluating this on a more recognizable face, so I play this result that we produced earlier this year too.
Now we've made them a lot more expressive. And not just simple things like looking left, right, up, down, but also the nonverbal cues that we rely on to communicate with each other and understand tone. Things like raising an eyebrow, squinting, widening my eyes, or scrunching my nose. You know, these avatars are way better at capturing those subtleties that define physical interactions. They're just much more natural. And being able to control the lighting on the avatars adds another dimension of life to them. When we move the light around, you can see how it interacts with my hair, it reflects on my skin, and you can even see it in my eyes. Now, these are awesome, but they also take a really long time to generate. So we're working on something that's a lot quicker for people to use.
We were criticized that he seemed more expressive than he does in real time. I'm not sure if that's a criticism or not, but I think it is. All right, so the research that we've been doing since 2017 has been along the lines of minimizing distortion. like how do we minimize distortion and how do we minimize latency? These have been the two principal sort of lines of research. Like how do we do those things? So I'll talk a little bit about the first change was how do we get more expression in these systems in real time, right? So what's the challenge of AR? So if you look at this, this is, if I'm wearing a headset, it's very hard to tell what the person's face is doing. So I'll say, imagine what my face looks like while a sensor gives you that data. I think reasonably, if I were to look at that, it might be that I'm smiling. But actually it isn't that, right? So it's much more neutral than that, and it looks that way because of the point of view. And that's the challenge that we have to solve. And so the approach that we took was to say, from an input and output perspective, this is the target that we have. This is what the cameras sense on the headset. And we have an avatar that we can deform and change its state, the state of the encoder, the viewing direction, and the lighting. And we want to try to make it match this by minimizing distortion once again. So what do? We have our differentiable renderer, and we can vary the code to be able to render it from the point of view of the cameras that are on the headset itself. And then through our lighting model, we can change how it looks and minimize once again pixel to pixel what the person was actually doing. And through optimization, we can actually try to change the state of the code to say what the person's facial state was to be able to minimize error against these pixels. What you see over here is a pixel by pixel error. And this is an interesting result because you can actually see gradient descent on a person's face. So it's going to move from a sort of neutral expression and try to find what expression matches this particular one. And as you see it, you'll see the error minimize on this on a pixel by pixel basis as well. So let me play that. Sorry. So you can see he changes his expression to match this one. And as it changes, as it's searching over it, the error minimizes as well. See, he's looking left. He closes his eyes. And on the face of a person, you're seeing the optimization actually happen. It's kind of interesting. And in this way, we're able to, even though we don't know what the person's face is actually doing, there's no target, we're able to supervise and provide sort of like goals for what the encoders should actually learn to do. And here's an example. I'll now swipe between what the system thinks the face is doing and the raw images that were captured. Here are the raw images, and I'll play it, and you can see it tries to match as closely as possible what the person's face is doing while he's moving. All right, so this is the end-to-end system. There's an encoder that takes the feed from the cameras, produces a code, and then that code is then transmitted and it's decoded according to the view, the transmitter's state, the receiver's state, and the environment to produce what the transmitter sees. This is the end-to-end pipeline of a Codec Avatar. And this is the result. This is Codec Avatar 1.0. You can see this conversation between myself and Danny.
Well, what can your face do? Can you show us?
Well, I've always hoped you would ask me that question. So I have some pretty good, I think, mouth movement.
How about your eyes? Can you look left, right, up, down? Good.
Yeah, I'm gonna be surprised. Ah, ooh. I think one of my favorites is puffing my cheeks.
The mouthwash commercial.
And rolling my tongue.
That's pretty good, actually.
Yeah.
Good.
Yeah, not a lot of people can do that.
So that was kind of the next step. We were able to get much more expressions in real time between two people talking. And then the last one was a move towards more of a volumetric style of rendering. We got much more detail on the eyes, and the relightability that I talked about, we were able to implement that in real time as well. So this was a new sort of representation that we presented in 2021, which is called a mixture of volumetric primitives. In essence, it represented any person's avatar as this unstructured collection of neural volumes, that when you rendered it, it produced the avatar that you saw. So I'll show a result. So this is a video that we produced as well, so let me show you.
Hi, Autumn.
Hey, Jason. To give you an idea of how true to life the 2.0 codec avatars are, we wanted to show you us live first, then show you the avatars.
Ready?
Ready?
Okay, let's do it.
Wow. It doesn't matter how many times we do this, I'm blown away every time.
Yeah, the 2.0 codec avatars are something else. We've made them a lot more expressive. So now not just simple things like looking left, right, up, and down, but also the nonverbal cues that we rely on to communicate and understand tone. Things like squinting my eyes, or widening my eyes, or raising my eyebrows, or scrunching my nose.
Yeah, these avatars really capture the subtleties of face-to-face interactions. Yeah. They just feel way more natural.
Yeah.
And also being able to control the lighting on these avatars really adds a dimensionality to how lifelike they feel. Mm-hmm. If you move lighting in the environment, you see it reflect off my skin, hair, even glints in my eyes.
Yeah, this is awesome, but we still have a lot of work to do before it's ready for everyone to use.
Yeah, that's right. They're super realistic, but they take a long time currently to generate. So we're working on something quicker for people to use.
I think we can debate whether this was more realistic or not, but our salesmanship has certainly improved in the last 3 demos. I think from speaking about iteratively, really reweighted least squares to selling how good this is. This, if you couldn't tell, was a produced segment by the product team. All right, but this was in fact actually the first cross-country call that we had. In other words, this was actually flowing over the internet, and this was a call between someone in Pittsburgh and somebody else in Seattle. And once again, I'll say, like, if you experience this inside VR, this was, in my view, when I make eye contact with Jason with the system, it was the first time I felt like we had crossed the uncanny valley in real time with a real person. So that's been kind of like the story over the past kind of few years, where we've pushed to minimize distortion, going from the face to getting higher quality eyes, and now moving towards the hands and the full body with the background as well. And all of these have been sort of like enabled by capture systems that I've talked about, right? I talked about Mugsy. So Shopticon is the system we used for the full body. And this was similar to Shopticon, which is about 1.5 meters in radius. This is more like 6 meters in diameter, and it has cameras all around once again. And in it, we can view the person from any direction and once again reproduce their avatars, their codec avatars for their full bodies. This is an example of what that looks like. We moved from more vector-based codes to convolutional codes. So the entire thing is a fully convolutional, actually encoder and decoder. And there is an entire pipeline which I didn't talk about, which takes the data from Mugsy for the head and does 3D reconstruction, key point detection, tracking at the highest levels of precision to allow us to be able to capture all of those subtle details that we need to capture. We do the same for the hands, and we do the same for the bodies as well. Each of these have their own sort of individualized pipelines that some examples over here of reconstruction. So this is frame by frame multi-view reconstruction. And because of the resolution of the cameras, there's no need for any infrared projection, none of that. Tracking is highly precise, so you see over here, this once again, just to give you a sense of, like, just pick any point, and this is the side of the face. We're able to really capture the subtle details of movement that the person does. Explicitly capturing the eyes and the teeth, because especially when you're looking at a person's mouth, it becomes very apparent if it's flat or if there's actually some detail inside there. Hair is a very important part of people's identity, or so I'm told, and so we have this sort of tracking, and it's once again the goal here is not for it to look right, but we want to actually get strand by strand accurate reconstruction. We want to be able to reproduce what the person's style actually is in real life. Here is an example of some hair rendering that we were able to do with dynamics to some extent. But you can see as she moves, the distortion in the reconstruction increases. It's an area of important work that we have to look at. Hand tracking is an important one. And while there's been a lot of progress in recent years in capturing single hands in the wild, capturing, like if you notice what any one of you right now is doing with your hands, they're not like that. You're either touching your hands or you're touching another part of your body with your hands, right? They're always resting, they're always in contact, and being able to capture that sort of movement, particularly with content, is extremely challenging to do visually. And the systems that we have, Mugsy and Shopticon, allow us to capture with some precision what this is. And while we're not able to do this right now in real time, this gives us at least a way of getting supervising signal to be able to learn, to create systems that can learn to get much more subtle detail of the hand and other parts of the body, like crossing your arms or putting your hands on your hips. This is an example of rendering codec hands. And our perception of our hands is probably not as acute as faces are. So when you actually see these in VR, they are like surprisingly realistic. And of course, the fact that they're severed from the wrist make them surprisingly creepy as well. This is an example of a rendering. And then finally, of course, full bodies, right? This is the result I had shown earlier. The result is also like, this is a volumetric rendering. And you can see over here quite a bit of detail is captured. This particular one is mesh-based, but nonetheless, you can see it's able to get quite a lot of detail on the person. The last thing I'll talk about, which I haven't spoken about much, is audio. So that's an important aspect of feeling like you're there with a person. Directionality of the sound, how it reverberates in the room, that gives you a sense that you're actually there with a person too. So this is another capture system that we have called Hearsay. And just like we have Shopticon and Mugsy for the visual field, we have this for the acoustic field as well. So I'll show what this looks like. Each of these ears that you see has a microphone inside of it. And so it's actually a space filled with these ears with microphones inside of them. Why do we have these ears? It's because your ear and the side of your head actually change the incoming audio wave, and that's what you actually hear. So this gives you an audio signal which is much closer to what you'd actually hear than what a flat microphone would. And using this, we also developed the first neural rendering system for audio, which this was a simple example that we published in iClear, where you can take monographic audio and the place in which the receiver is hearing you from. So where you hear someone from, you take mono audio of the transmitter, your particular pose with respect to where the audio source is from. There are three sort of transforms. One is a geometric warp that just says time of flight. How far is my left ear from you as a source? How far is my right ear? And changes the audio signal for each ear. And you can see that sort of the dark blue and the full dark orange are the target, as well as the transformed signal with respect to the left and right ear. So the light signal is the ground truth, I believe, and the dark one is the transform signal. And then there's a neural warp correction, which takes into account the fact that the head is solid, and as the audio waves move across your head, they get slowed down. And then the final, and you can see this increases the precision of the match. And then finally, the sound generation is directional, and sound reception is directional as well. And so there's an attenuation function over there that it corrects for, and it matches the audio quite well. So now if you were to hear what's being said, you actually feel like the sound is coming from a source in the direction it should come from. And as you move around, if there are multiple sound sources, they come from where you expect them to come from. This is an example of this. So what you're seeing is in VR, there's a headset. There's a head of a person, and she's singing. And what you're seeing on the right are the left and right audio levels. So as you move around, as you move to the left, obviously the right signal should go higher. As you move to the left signal should go higher. So I'll play this for you to see. So this was part of what we call the Codec concert demo. In this, we had an a cappella group come in, and individually they recorded different parts of the chorus, and then we synthesized this inside of VR directionally. So when you are in VR, you actually feel like they're performing for you. And as you move around in the space, it feels like you're moving around with the group performing. So I'll play the individual input that we recorded in our various capture systems.
While we seek mirth and beauty, and music light and gay, there are frail forms fading out.
So this was recorded, and then inside VR, once again, I'll play the video of it, but I can't describe the feeling of actually hearing this in VR and feeling like there's a group of people singing to you. This, to me, more than almost any other demo I've seen, makes me feel like, yes, this is how I would like to experience concerts in the future. So I'll play it to you, but with this caveat, so if you can normalize that. What you'll see is Alex, one of the authors of the paper, he's moving around in VR, and there's the replication of these different performances that they were there. And it's played back from his perspective, the audio as well as the video. So obviously the reason why there are two people here is because two people sang multiple parts, of course. All right. So that's it. This is kind of the challenge that I talked about earlier on how do you define distortion and how do you disentangle these sources that we want, the transmitter, receiver, and the environment. This is what's motivated the design of these systems that we've built. And there's ongoing research in future systems as well, where we try to disambiguate these together between the audio and visual fields. So I mentioned this as the definition of codec avatars, but there's a very important piece that's missing in this, which is that this is actually a closed dynamical system. When you're having a conversation with someone else, you're not talking to a person. You're engaged in a conversation with people, and information is actually flowing continuously between two people. And it's really, I think, the right way to think about this is as a coupled dynamical system, exchanging information. And that's why minimizing distortion and latency is so important. Any distortion that's induced by the encoders on any side or latency disrupts the flow of information, and that's what we would feel when there's delays in VC or over an audio call. It disrupts the conversation. In a system like this, where you're in a room with multiple people, a stall or a delay or any sorts of distortion would fundamentally disrupt the interactions as we have them. So this is a kind of a core part of our research is how do we actually treat it in this way and fully minimize distortion and latency. So this was a description of distortion. That's mainly what I talked about today. There's a lot of work to minimize in latency. I talked to some students here who've been thinking about the concept of social prediction. Can we predict what a person is going to do in the future? And I think this way of viewing a social interaction as a dynamical system, exchanging information, a critical part of dealing with latency is to try to predict out into the future, not seconds or minutes, but even tens or hundreds of milliseconds. What is a person about to do? And if we can do that, we can reduce latency and make the conversations feel much more engaging. It's a very open area of research which we haven't sort of touched, but I would say this is probably the primary core of what we want to do. So I'll end with kind of what I think is a big potential. I think overcoming distance is only one form of physical distance, is only one form of distance between people in forming social relationships. There are many others, right? There are many conflicts we see between people socially. There are many people who have difficulties forming and maintaining social relationships. And I think a real kind of promise of this, if we're able to accomplish it, is that we'll be able to have computer mediation for the first time. We'll be able to bring the power of computation to make social interactions between people much better. Of course, with any such promise, there are dangers. There are kind of many threats to what this could do for society. But that's, I think, part of the research and the responsibility we have in doing this work. This was a quote that was actually said by Relighting and Taylor, two of the inventors and founders of the internet. I mean, really, there are many people who can claim to have invented the internet, but there are probably few people who have as much right as Relighting to make that claim, and few who have as much right to make the claim of inventing the modern PC as Bob Taylor. And this was what they said in 1968, quite a while ago. It's still not achieved. We're still not at a point where it's more effective to communicate through a machine. But I feel telepresence is something which is within grasp, where we are maybe like a decade away from accomplishing that. But when we can, I'm really looking forward to seeing this prophecy fulfilled. With that, I'd say like this is the work of a large number of people in the Meta Reality Lab in Pittsburgh, without whom the work would not be possible. I've summarized a few of the papers which we've published along the way, in case you're interested, along with my email, and I'm happy to answer questions if we have time. Thank you.
Hi, Vijay.
What kind of delays are you getting right now? What kind of, to do the demo that you just talked about, how heavy is the VR mask or the device, and what kind of power consumption does it have? Is it going to burn people's faces because it consumes so much power?
These are all excellent questions. So, I mean, I can give you the numbers. Probably it's not, I mean, very meaningful for me to say is 700 grams. That's really, right. But what I mean is like, what does it feel like? What we found is rather than the absolute weight, how the weight is balanced on the headset is important. My sort of like, the functional question you're asking is how comfortable is it, right? Like how long would I actually want to be in one of these?
Like if you're doing cross-country communication, is your delay right now, is it like 100 milliseconds,
Right.
150,
Right.
200?
Right.
What is roughly?
Right. So I'll answer the first question. So maybe one proxy for your question of comfort is how long has anyone voluntarily had a conversation in one of these? The longest we've recorded without prompting was a half an hour conversation, which was like we were showing it to someone and they were just curious about how it worked and they ended up having a half an hour conversation in it. So that was the longest. I don't know whether it was comfortable for them at the end, but they did have the VR marks over here where they had those for sure. So I would say probably uncomfortably half an hour is where we're at right now. In terms of delays, it depends on the state of the network, right? So typically you see between 100 to 200 milliseconds of delay. Now, cross-country. What's the target for us, right? What should we target? So if you look at the literature, it says 120 milliseconds, approximately. Different papers say between 100 to 120 milliseconds, people can perceive the delay. But I think that this is like, in practice, almost certainly not true. Like if you talk about how much you can perceive, it might be 100 to 120 milliseconds. But what is the number that doesn't disrupt a conversation? That number is probably much lower than that, right? And it's not one which is easy to access. Like how do you actually figure that out? What is that number? It's not easy to know. My sense is kind of like looking at the work, probably in the 30 to 40 millisecond range. So it's not out of the question. It's not physically impossible. But we need to drive it lower down below that. I have heard that there have been some sort of research systems that have been built between cities like Berlin and London, where they actually conducted an orchestra with part of the people being in Berlin, part of them in London, and they were able to run this online with maybe like a 5 to 10 millisecond delay. So physically it's possible to build this. It's a question of whether, I mean, there's marginal value in it, and how practical it is to do it at scale.
Is the communication delay the dominant one, or is it the encode and decode?
Right now it is the transmission delay. That's the dominant one. But everything I showed you was I mean, that we showed cross-country was just the head. And both sides had 2 high-end GPUs and workstations. So the target is to be able to do this on device. That's a fairly big jump, and that's going to induce a lot of latency, and thermals, of course, are related to that. So we're still at least an order or 2 orders of magnitude from being able to do full bodies on the headset itself.
So the demo that you saw when they were just talking,
Yeah.
was that on GPUs off the person or on their head?
So there were GPUs on a machine. We have versions which are on device as well. The distortion is higher, right? And it's only the head. So the full body stuff was all on a workstation. The highest quality avatar faces that you saw, those are also on a workstation. But the higher distortion ones, we're able to get them on device right now, up to 5 people.
And this is using custom GPUs or
No.
off the shelf?
No, off the shelf. The one that's actually commercially available on the Quest Pros.
On the what?
On the Quest, the actual Oculus headsets, right?
Hi, thanks for the talk. For the gradient descent on face example that you showed for capturing people's expressions, how do you deal with the fact that the people's appearance might change after their capture, say they shaved or they've changed?
Right. So that's an excellent question. The first sort of like generation or two generation of these encoders were extremely fragile to that. Not just the fact that they may have kind of like some facial hair that grow or they may put makeup on, but even the environment changes would throw the system off. So what we've been doing more recently is taking multiple people's data and sort of like trying to come up with a more universal state space, meaning a state space that's shared across people. And by doing that, by sharing that space, the system learns to have two interesting properties. One is it gains robustness to those kinds of changes, but also there's a kind of like emergent structure to those codes. Like what do they mean? Because they're shared across multiple people now. Those are two kind of like interesting emergences. Now, of course, there are other tricks on building robustness to this, like just have augmentation of the data, but the identity augmentation was the one which produced the most stabilization.
Thanks for the talk. So when you're talking about minimizing distortion, my understanding is that you've been working on minimizing kind of photometric pixel-to-pixel distortion, and that requires having these really high-resolution cameras all around the person. But it seems to me for communication, you're really interested in minimizing the perceptual distortion. So there's these kind of experiments where if you turn somebody's head upside down, if you turn their eyes also upside down, it's perceptually very difficult to tell. So I was wondering, as you're moving towards developing systems that are lighter and more real-time, have you thought about how one might move from a photometric-based distortion metric to a perceptual one?
Right. So primarily the challenge with this is that the measures that you're talking about tend to be self-reported, like what do you think you know? Whereas if you talk to any cognitive neuroscientist or a neuroscientist, they'll tell you that a perception is kind of like thought of as the iceberg, right? Like what you're conscious of is the tiny tip, and most of perception is not happening consciously. We don't have access to what the person is actually perceiving or not perceiving. The only thing we have access to is like what they know of their perception, which is a very thin sort of sliver. So if we had access to reliable objective measures, absolutely, in a heartbeat, right? But we don't. And then the next best proxy is to try to replicate what they actually did. So that was a bit of the discussion I had about the behavioral change. Like if we actually had measures of perception that we could say, okay, minimize this perceptual loss and the behavior of the interaction would not change. That would be the ideal thing. But we don't have any means of directly measuring that. So I would say this is really a sensing problem. In the absence of those, what we say is it's sufficient if we're able to replicate what the person actually did, and that's what we can do with sensors like a camera.
Thanks for the talk. So when I think about communication, it often involves some sort of like collaborative work. So like for instance, when I meet with my professor, it'll be very helpful to have a whiteboard so that like we can write. So do you think like based on your presentation, you sort of started with the face avatar, body, and reached to audio, like step by step. Do you think like all modalities are sort of disentangle and you can like solve it each one by one, or do you sort of like envision or like have a clear vision on like how those things will come together in the end?
Yeah, so I wouldn't say that we have a clear vision of how they will come to the end, right? Like ultimately what would be great is if we had haptics in there as well, right? Like if we had smell in there as well, like all the senses. There are like varying levels of maturity of each of these areas of research. Fortunately, or maybe somewhat in a biased way, if we say vision and auditory senses are the primary senses of interaction, those are the most mature. And we actually already with the current systems that we have in VR, there are tools for whiteboards and keyboards and things. They're not bad, actually. There are still, I think, some ways to go in terms of precision, but they're not bad. You can have a kind of like a discussion on them. So those pieces exist. Trivially, we could put them all together and make it work. But I do think like the maybe what I would say the insinuation of your question, like the real power of this would be if we can make sure that they are all coherent with one another, right? Like the brain we know is a fusion engine. Like it takes in many different sources of information, fuses them to get our impression of reality. absolutely, the more modalities we can fuse together, the more true like suspension of disbelief would be, without question. Right now we're focusing on audio and video with the avatar. Once you do that, as you say, we'll move on to the next ones. At each opportunity, we'll see how to fuse them. But at this point, I would say we're just at the point where we have some parts of vision, some parts of audio under control.
Thank you for the wonderful talk. So I just wanted to go back to your a cappella example. I noticed that you were taking a capture of each person individually, and I was wondering if in practice there was a difference between these individual captures versus having, say, a set of 4 people in an a cappella setting, and then doing a demo of that in the 3D space.
So fortunately, audio sound is additive, which means as a sound field, if you have multiple sound sources, you add them, the superposition is actually what we'd expect. So in fact, the way we want to use this was a playback of what people had done, as you said, individually. The latest systems we've developed now actually allow 4 or 5 different people to talk to a person simultaneously and get localized. It's still, the distortion is a bit high because we've tried to do it on board, but it actually works quite well. If we can do it like on the device so people can move freely, I think that would be the goal. We haven't reached that point yet.
Last question from anyone?
Once again, thank you for the talk. It was like really well done. Appreciate you coming out here to do it. So while you were talking about kind of the sort of like building in some appearance invariance, like if someone grows a little bit of facial hair or whatnot, I was thinking like, have you explored doing non-photoreal like editing and like exploration of these codec avatars that could be interesting, like the way people like putting on filters on video or photos?
Yeah, without question. I think that aspect will actually be easier with these 3D avatars than it would be for filters, because obviously everything's registered, everything's high dimension. So we've done a little bit of it, but not spending a lot of time on it, because I just feel like that would follow quite directly once we've had it. The things we've tried are, for instance, clothing. Like we've added clothing, simulated them, seen how it goes. For some reason, hair was one. The team took a lot of pleasure in giving me various types of hairstyles. So we've tried that as well. But things like coloring lips and adding a beard, those sorts of things are, it depends on, some of them are easier. Lipstick, makeup, those are easier. Beards, hair, that's harder. Especially when you think about relighting. So I expect that those will be the very first things we try. Then there will be interesting questions on how far do we move beyond that, and what should be allowed and what shouldn't be allowed. And that starts to touch in a little bit of the privacy, integrity, ethics sorts of questions, right? Most people will agree that you should be allowed to put makeup on or change your hairstyle. Those seem like legitimate changes. But how much change should be allowed? Can someone have the equivalent of a plastic surgery? Maybe. Should someone be allowed to look like someone else? Probably not. Where's the line, right? These are sorts of questions which I think we'll have to face, and there's kind of real research involved in that. Yeah.
Thank you.